So, hello everyone. My name is Vinit, and my research partner's name is Suhas, and we belong to Christ Deemed University, Bangalore. And our project guide is Dr. Arun Kenneth. And the topic of our interest is cosmology, dark matter, theoretical physics. And here are we presenting the dynamics of compact dark matter objects. So, just to begin with, we know that dark matter is like non-baryonic matter, which is does not interact with light. It only interacts gravitationally, and it makes up 27% of our universe. Here we are considering candidate of dark matter as WIMPs, weakly interacting massive particles, which have the mass range from 10 gigaelectron volt to 1000 gigaelectron volt. So we have tried to constrain the mass of that WIMPs. Our Some of our observational evidence is using liquid xenon, and other way of constraining is microlensing, gravitational microlensing. So yeah. So coming to the results, we have found that for xenon 100 results, the scattering cross-sectional area comes in the range of 10 power minus 38, and the latest is 10 power minus 46 centimeter square. That's the cross-sectional area from the Panda X2. And calculating the mass of dark matter objects, which are made up of WIMPs. So we are considering Chandrasekhar mass. Basically, it tells you the mass limit for the stable objects. Here, the MD represents the mass of our dark matter particle, as I told, 10 gigaelectron volt to 1000 gigaelectron volt. So we consider this range and we calculate the mass of our compact dark matter object for different range, 10 gigaelectron volt, 100 and 1000. So we see it comes in range of 10 power minus 2 Mson, 10 power minus 4, and 10 power minus 6. So here's the graph that shows how the mass of dark matter object varies with respect to dark matter particle mass, which is from 0 to 1000 gigaelectron volt. And the objects that we are considering are like dark matter objects. These are not MACOs, which are like massive astrophysical compact halo objects. And the reason is that we hypothesize objects which are free floating, and the range is supported from the literature. And these objects can be of the planetary size and planetary mass, and we try to constrain the mass. So the way we constrain the mass is using, as I told, we do it using microlensing. And Einstein radius is the radius that forms when the gravitational lensing happens. So it's the radius of the object, the radius of the lens that has been formed. And we know the formula for Einstein radius, which is dependent on mass and distances. Here, dl is the distance to the lens. We are considering lens distance from Milky Way, from our Earth to the dark matter halo, which is around 20 kpc, and our source distance is LMCs, which is around 50 kpc. We also calculate the microlensing time scale. It tells you for how much time the microlensing event takes place. Basically, it tells you for what time the dark matter object goes in front of LMCs. And here we make use of the event rate equation. Here, epsilon of t tells you the efficiency. ds tells you the source distance, as I already told. V naught is the orbital velocity at that distance, which we know for like Milky Way galaxies around 220 kilometer per second. Rho dm represents the density of dark matter at distance. We have calculated that separately. And using this equation, we find the number of microlensing events that takes place using the given formula. Here, the N star represents the source stars. T observed represents the total time for which they have been observed. We integrated twice. The second way to calculate the number of events is using optical depth. Optical depth tells you the probability of that event happening at a distance for a particular mass that is given by tau. And using tau, we also calculate events, and that is using LOS survey. So here we consider LMC, which is 50 kpc, and T is given by this simple formula. Since we are considering two methods, so our results are a little bit different. We find that using the event rate equation, we got around 96 events, and using the optical depth, we got around 179 events. So from calculated number of events, we can rule out that 10 power minus 6 and 10 power minus 4 Emerson masses cannot be considered. Only the mass range, which is in form of 10 power minus 2 Emerson, will be considered. That is the constrained mass for our objects using the microlensing data will be 10 power minus 2 Emerson.
So hi, I'm Suhas and I'll be continuing the work. Now that we know that our feasible object mass is 10 power minus 2 solar masses, we'll see our feasible objects dynamics like radius, temperature, due to the hydrogen and helium layers which will get accreted. So let's start. The radius of the object, which is 92 into h cut square by m to the power of 1 by 3, which where m is the mass of the object and md is the dark matter size. We calculate the radius of our object to be 10 power 5 centimeters. So due to this object's gravitational pull, hydrogen and helium will get accreted on top of the dark matter objects. We'll use this formula to calculate the how much total mass has been accreted, and the density of hydrogen and helium are 3 into 10 power minus 22 gram per cc and 2 into 10 power minus 21 gram per cc. We got the mass of hydrogen to be 10 power 22 grams and helium to be 10 power 23 grams. Next is the when they are accreting due to the gravitational pull and high density, it will start to heat up. So its temperature was found to be 10 power 11 Kelvin and 4.77 to 10 power 11 Kelvin, which is 4 times the hydrogen layers. From this, we can calculate how thick the layer will be, which is given by Rg into T by G. Rg is the gas constant. The hydrogen layer will be 5.18 centimeters and the helium layer will be 34.5 centimeters. Using this, we go back and calculated the density, which is given, which was found to be 10 power 14 gram per cc and 10 power 15 gram per cc. Now the object cannot keep accreting. There will be a certain limit to the mass accreted, which is given by the 4 pi r square h into rho. H is the thickness or the height, which was found to be 10 power 26 grams and 10 power 29 grams for helium. So the Eddington luminosity for our mass will be 2.052 into 10 power 36 ergs per second, which we will use to calculate the energy released by hydrogen and helium. The extra mass which is accreted will be ejected away, and the energy released will be mass accreted into energy released per gram, which is found to be 10 power 45 ergs and 10 power 47 ergs. Now that we have all these parameters, we will try to solve the Galactic Center GeV Electron Volt Excess. People have seen extra GeV Electron Volts from the disk of the Milky Way at its center, but its source is not yet known. It can be dark matter annihilation as well, but here we are telling it's because of this dark matter objects. Since we know its temperature of the layer, we can calculate at what energy it will be releasing, which we have found to be gamma rays, which is coinciding with it. But in order to detect this, we also have to know that this burst which is coming should be detectable. So we have to find the time scale of it, which is found by energy released by the power. We found a time scale of burst for our object, which is 10 gigaelectron volts dark matter particle, to be 320 seconds and 2 seconds, which is detectable. But this was only for our feasible mass size, which is 10 gigaelectron volts, which is corresponding to 10 power minus 2 solar masses object. But we also went back and constrain it for our range of particles, starting from 5 gigaelectron volts to 12 gigaelectron volts. And the time scale for the H layer is from going to from 200 seconds to 1200 seconds, and for the helium layer it will start from like around 1 second to 9 seconds. So what we'll do next is match it with the observational evidence which we have found and see if we can solve the giga electron volt excess as well.
So yeah, after going through the admixture we have a problem called the missing Baryon problem, and it tells you that since the Big Bang, the predicted amount of matter, baryonic matter, has been 30% less. Here we see that the warm, hot interstellar medium corresponds to around 30 to 40%, including both Lyman alpha and OV69s, or 6 and the galaxies corresponds to around 9% of that. The circumstellar galactic medium corresponds to around 5%, and the missing baryon, which has been predicted and not been found, is around 30%. So we consider our dark matter object, which is of 10 electron volt mass, effect WIMPs mass, as the idea that this WIMPs compact dark matter object can be the solution for the missing Baryon problem. But since we cannot directly say that uh, the dark matter object has been completely made up of WIMPs, we consider the fractions that maybe it has the fraction of 0.1 to 0.9 fraction of baryonic matter inside the dark matter. So we consider those fractions of dark matter objects. And here is the equation of the radius of that object, which has both the baryonic matter and the dark matter. And this equation we get using equating the pressure degeneracy of dark matter objects and the baryonic matter. We also consider the radiation pressure, but then we ignore it for the simplicity. It does not make a significant changes. So here we consider MD as our dark matter particle mass, MP is mass of proton, and the effective mass is given by this. And we are considering F1 minus F is of course the fraction of dark matter, F being the fraction of baryonic matter. And here the M represents the mass of that compact objects, where M cube of PL is the Planck mass. So using these equations, we get to the fraction of dark matter, fraction of baryonic matter. We have the effective mass. We get effective mass, like combining both, and the mass of that object and the radius of that object. And this is only for 10 gigaelectron volt, which we have constrained earlier. So plotting that with respect to fraction of baryonic matter with and mass of object on the y-axis, we get a plot like this. We see that as the fraction of baryonic matter increases, the mass of object rapidly increases. And here we are making use of microlensing data again. We calculate the Einstein radius, we calculate the microlensing time, and we calculate the events for these objects for the different fractions and the different masses. And events 1 and events 2 represents the different methods, as I told before. Events 1 is using the event rate equation, and events 2 is using the optical depth. So we come to the fact that 0.1 and 0.2 fraction can be ruled out. It does not matches with the observational data. So we consider 0.3 to 0.9 baryonic matter fraction for our next. Yeah, here we calculate the missing mass, since we know the total masses of the universe is 10 power 56, and 30% that is missing. That corresponds to around 10 power 55 gram. And then we can just pull out that baryonic matter is FB times the mass of object, our object that we have calculated, and we can say how many such objects are needed of that mass to fill 30% gap. Lastly, we get to the percentage of it. So yeah, here are the results that tells you for different fractions, for different masses, so many objects are needed, and baryonic matter comes in the range of 10 power 31. So that tells you the percentage contribution of that fraction in the sense, what fraction of baryonic matter is inside the dark matter. So these are our results, and here are our references. We uses different paper to constrain the masses of our objects. And yes, thank you very much.